All right, folks. What we want to do today is come up with a system for approximating any function, like the cosine function, using a polynomial. That's possible. So I want you to think about it. You know the cosine function, you know what it looks like. If you had to come up with a polynomial that perfectly approximated the cosine function, how would you start? I don't know. Maybe what you would do is think about where are the zeros of the cosine function. This is a very identifiable feature. And then maybe try to produce a polynomial that has at least those zeros, right? Okay. How do you get the zeros to be what you want? Well, you know what the zeros of cosine are. They're like negative 5 pi over 2, negative 3 pi over 2, pi over 2, negative pi over 2, pi over 2, 3 pi over 2, 5 pi over 2, and then just keep going on the outside. So how are you going to get a zero of any function? Well, how do you find the zeros of any function? You set y equal to 0. So what would solve this equation if y equaled 0? Negative 5 pi over 2. That would be a 0, right? These are all the zeros. What degree polynomial did I put in here? That was 1, 2, 3, 4, 5, 6. 6-degree polynomial. So maybe it'll approximate some of the cosine function. But it's only going to capture 6 of the zeros. Also, in a cosine function, all of the zeros are what kind of zeros? Crossing or touching? Crossing or touching? Crossing. So what must the multiplicity of each of these guys be? Odd. Well, this is fine. This is multiplicity 1, multiplicity 1, multiplicity 1. So they'd be crossing zeros. Let's see what happens when we graph it. Okay, if we graph it, look, there's our sine function in the zoom standard window, and this is what we're seeing about our polynomial. At least our zeros are right, but the rest of it's terrible. We're going to have to dramatically change the window, I think, to even see what's going on. Let's change the y max and y min. What about negative 1,000 to 1,000, just to see if we're even in the ballpark. That's what our sine function looks like. It looks like a line now. At least we can sort of see our polynomial. I don't think 1,000 is going to cut it. Let's go 5,000. Negative 5,000 to 5,000. Graph that sucker. Oops. Let's try again. Sine function, and here comes our polynomial. Wow, that's not even going to do it. I have to come down way down. Okay, maybe we're going, I don't know, 500,000? That might be way too much. Wow. All right. So the problem with our function, let's go back to our zoom standard window. The problem with our polynomial, as you can tell, is that it's just so stinking stretched this way, up to an order of like 500,000. So we have to compress it. How could we shrink it? Well, to stretch a function, you just multiply it times like 10 or 20 or 30 or 40. To crush it, you divide it by that, right? So let's just do that. Let's just divide by, what did we go, 500,000? Let's see if that even was right. 500,000. See if this crushes our polynomial again enough. Excuse me, second insert. There we go. So I'm just compressing our polynomial. See if it comes even close. Okay, it's too compressed, as you can see. Too compressed. It looks like the line now. So we need to maybe go 50,000. Still too compressed, huh? Okay. How about 10,000? Ooh, that's looking much better, isn't it? Maybe still too compressed. We'll go 5,000. Okay, I'm sort of feeling it. Now the problem is, of course, cosine's going up then down, whereas this polynomial is going down then up. How can I fix that? Just flip the graph over. How do you do that? Put a negative sign in front of the cosine function. Second insert Negative? Try it now. What? That's really good. Wow, good guessing on our part. So look, out here, as x goes to negative infinity, terrible approximation. Terrible approximation as x goes to positive infinity. But in this localized region, I think we graphed it from, well, here's 1 period's worth, and here's a 2nd period's worth. Within, like, say 3 periods worth, we're doing pretty good, and within 2 periods worth, we're awesome. I mean, we're doing a great job approximating, right? How can I make this better? Well, I could just come in here and add some more terms, like x plus 7 pi over 2, x plus 9 pi over 2, and over here, x minus 7 pi over 2, x minus 9 pi over 2, and what will that do? That'll mean when I go to my graph, I'll be able to get the next hump, and then the next hump. Just keep adding terms, and it's going to get better and better approximations. Now, we just did this willy-nilly, thinking about, well, what are the zeros, and then guessing on the compression. What Taylor will do, what the Maclaurin polynomial will do, Maclaurin polynomials are just polynomials, but it's a systematic way to come up with a polynomial that perfectly approximates another function. It's a very simple, systematic approach. Okay, so we're going to explore that in the next video. Thank you.